Hello, welcome back. The last topic I want to cover in PN junctions is the differences between an ideal diode and a non-ideal diode. So far, what we have seen is what we refer to as an ideal diode. And the expression that we have derived, this current expression, current density is equal to Js exponential QA by KT minus 1. This is actually called as an ideal diode equation. Okay. Well, because it's an ideal diode because we have made some assumptions, and those assumptions are that when we are calculating the currents, we had the depletion region, right? So we had this XP minus XP and XN. We looked at the diffusion currents here and here, but we said that there is no change in the depletion, okay? No change in the depletion region currents, okay? But well, you're introducing holes and electrons, right? Excess holes and electrons across the depletion region. So there's going to be some recombination happening, okay? So, and there's also going to be some generation happening because it's completely depleted of carriers. So there are some generation recombinations that can happen in the depletion region, which we have ignored. And today we'll see the effect of that. Okay? And also we assume that we have low level injection, by which we mean, let's say you're injecting a hole into the number of holes into the into the N-type semiconductor. We said that the injected excess carriers are still going to be less than the majority carriers, or N naught. N naught means electrons in the N-type semiconductor at equilibrium. Okay? So it's still going to be less. But if you try to inject more holes, then we are going to have a region where even the majority carrier concentration is going to be perturbed, and then your current characteristics will be slightly different. Okay? So we made these assumptions and we derived this, and you must be familiar already with this sort of a diode-like action. It's kind of linear in the small voltages. In a finite range, it's going to be linear, and there is this threshold voltage that we can define, Vt. So to understand the non-idealities, we'll try to plot it in a slightly different form. So I'll plot it in such a way that, in the forward bias, I'm plotting log, okay? Forward bias, I'm plotting log of current versus applied voltage. In the reverse bias, I'm just plotting the linear current, okay? Linear current versus linear voltage, okay? It's just a mixed graph. That's why this small break in the axis. So if you take a logarithmic J, take the logarithm of current, what you will get, you essentially will see that the slope is going to be, well, it's quite small here. So the slope is basically Q by KT, all right? So you're going to get a straight line if it's an ideal diode. And we'll quickly show that this is never going to happen. Okay. All right. So one of the first non-idealities that I would like to discuss is what is known as a junction breakdown. Okay. So we are applying a reverse bias voltage into the PN junction, and we are assuming that this current is going to be constant, like this, right? And we never specified how long it's going to remain constant. But it turns out that after a point, the diode breaks down, there's a sudden increase in the current. This particular phenomenon is called as junction breakdown. Okay? So you can't simply keep extending the depletion region as much as you want. At some point, it's going to break down. And what is that point? We will see. Okay? So to understand junction breakdown, we have two processes that are important. The first process is what we know as the Zener breakdown. Zener breakdown. And the second one is called as avalanche breakdown. Okay. So what happens is a Zener process. Let's say if you increase your depletion width, or you apply more and more reverse bias voltage, your bands are going to become steep because you're going to have larger and larger electric field, right? So there is more charge uncovered, so larger peak electric field, so more band bending. So bands will bend. And this is a schematic illustration of how the bands could bend. Basically, you have a large barrier, right? This was Q into VBI plus VR. I'm assuming that this is basically negative voltage. Sorry, minus VA, and this is basically, yeah, that's why it's going to be positive. The total is going to be positive, so it's going to have a large barrier. Now what happens if you have such a large barrier? It turns out that you have at a position, for example, here if you look, you have a large constant. You can have basically the valence band is full of electrons, right? It's all, electrons are all bonded to the lattice. If an electron is absent, then we call that as a hole. But in principle, you have a lot of electrons. And the electric field is directed in the negative x-axis, right? This is the direction of electric field. So in principle, your electron can actually go from the valence band into the conduction band of n-type. So this is basically electron in p-type semiconductor. And here you see, we have studied as you go deeper, lot of states available. Right? It's all empty. You have lot of states in the conduction band available. So what's going to happen is your electron is going to go into the conduction band of the n-type. Okay. So this is basically this process. So basically is called as tunneling. So electron tunnels into CB of n-type semiconductor from valence band of p-type. Remember, we mentioned tunneling in the first couple of lectures, right, in passing actually. Okay, so what is the tunneling? So well, if you have so this is the energy barrier, right? As you increase the voltage, the energy barrier becomes narrower and narrower. That's all. Okay, but you still have a barrier. So essentially, if you have an energy barrier like this, and you have an electron incident on it, what happens? We said that in classical mechanics, there should not be any probability of finding electron here, but quantum mechanically, there is a certain finite tunneling probability. It could be 10 power minus 6, something, 10 power minus 4, whatever. There's going to be some finite non-zero, okay? Non-zero probability. What happens if you have that probability? Well, if you have 100 electrons, one of them is going to come. And valence band is full of electrons, right? We have 10 power 22. That's the number of lattice atoms, right? And each of them has 4 electrons, right? So they can tunnel into the other side. So there can be a lot of current that can have flow. And this happens, it depends on the barrier width. Okay. If your electric field is increased, or rather applied voltage is increasing, as VR increases, electric field increases because the gradient is stronger. And because of that, tunneling increases. Tunneling increases. So this current is called as a Zener breakdown current. So we call it also band-to-band tunneling. Just a fancy name of saying band-to-band tunneling. Essentially saying that from valence band of p-type to conduction band of n-type. That's a band-to-band tunneling. Okay. So this is Zener breakdown. We also have another type of breakdown which we call as avalanche breakdown. We've already seen that here there is an electric field, right? There's a strong electric field here. And whenever you have an electric field, the carrier acquires a lot of energy, right? As it travels, we have seen the kinetic energy of the carrier. So if you, let's say, take an electron, let's say from here, it's going to travel and it goes deeper, it has a kinetic energy. And with that kinetic energy, it can knock off an electron from the lattice, right? So what it can do is, it can take, for example, an electron it can knock off from the lattice and create a hole in the valence band and create an electron in the conduction band. So, and then there's also the original electron, right? So, basically, high energy electron creates electron hole pairs, electron hole pair. One electron, as it acquires kinetic energy, it will create one electron hole pair. It depends on the amount of energy it acquires. And then these two electrons will travel again in the band, right? In the conduction band, they're free to move about. And as they acquire kinetic energy, they create more holes. And then you end up getting more electrons. Okay? So this process, so basically one electron will create two electrons will create 4 electrons, and 4 will create 8 electrons, and so on. I mean, it just multiplies, right? It depends on how many electrons it's creating. The multiplication factor we call it. For each electron, how many new electrons are being created. Of course, there are going to be holes also created, and holes effectively will go in this direction, electrons will go in this direction, and they keep getting multiplied as it travels across the crystal. Okay, so you have, if you have a large reverse bias, okay, at large reverse bias, current increases abruptly due to avalanche multiplication. Avalanche multiplication. So by which we mean that essentially each electron is going to create more electrons and so on. That's why we call it avalanche. Okay. All right. So this is called as avalanche breakdown. These are the two main junction breakdowns that we see in the PN junctions. And how does it reflect in the IV curve? Well, we saw the initial ideal IV, which was in the blue. Now I made it dashed curve here. If you have junction breakdown, we see that in the reverse bias, after some point, it simply increases. Okay. This is basically called as breakdown. It could be either Zener or avalanche breakdown. What exactly depends on the voltage ranges and so on, which is not important for us right now. The second type of non-linearity that I would like to discuss is basically the electron hole pair generation in the depletion region. Okay. So what happens? Let's say you have a PN junction. Let's say I have a PN junction this way, and I have a depletion region in between. Right? I apply reverse bias, and then the depletion width increases. But this is essentially out of equilibrium, right? Out of equilibrium. Whenever semiconductor goes out of equilibrium, it tries to come back to equilibrium. When you have excess minority carriers, they will recombine. When you have less carriers, it will generate. Okay. So EHPs generated to restore equilibrium. Right? So if you have electron hole pairs getting generated, we said the reverse saturation current, right? This was due to the availability of minority carriers. On the quasi-neutral regions, you will sweep away whatever carriers were available into the other side. That's how reverse saturation current was coming. But in addition to that, now you have electron hole pairs which are getting generated in the depletion region itself. And as the depletion region width increases, more and more carriers are going to get generated. Okay. So this leads to one form of non-ideality, which we call as, which we identified. This section basically is electron hole pairs, EHPs in depletion region. Okay. Basically this increases as W depletion increases with V applied increase in the negative direction, right? So as we go to more and more negative voltages, the depletion width increases, so more and more electron hole pairs are getting generated, and that's why there is this gradual change in the current. So this section we call it as electron hole pair generation in the depletion region. Okay. Well, I forgot generated here. Okay, here electron hole pairs generated. Okay. And the opposite phenomena happens at small gate voltages in the forward bias. So you see here, this was at small VA, forward bias, not reverse. What happens there? You're essentially injecting minority carriers. Okay, so you're bringing in, I'll put it in blue here. So you're bringing in holes here and you're bringing in electrons from this side. So they're going to recombine. Okay, so uh, excess electrons, excess N and P will recombine. Okay, but this effect is not very significant. It occurs at very, very small applied voltages of the order of, few kts. If you go to 100 millivolts or something, this is going to vanish. The reason is the diffusion current goes exponentially, right? So once the diffusion current takes over, after few kt, after few kts, I mean, 1 kt is basically 25 millielectron volts. Few kts, let's say 100 millielectron volts. After 100 millielectron volts, or zero point 0.1 volts, diffusion is going to take over. Diffusion becomes dominant current, and hence semiconductor diode shows ideal. Diode shows ideal IV or JV, whatever you want to call it, IV characteristics. Okay, so this is basically the region 3. This entire thing. I'm sorry, I changed my color. I should have maintained in the same color, but essentially this is, okay, and this is this. Okay, so as this is a third non-ideality that you will see, but I would say that this is not very significant effect because there's a lot of forward bias current. Diffusion is very strong. We saw that it can be few amps per centimeter square. It was significant in the reverse bias because the current was picoamps per centimeter square, and then any small addition is going to show up. And remember, this is actually linear. This is linear, and this is logarithmic. So you don't, I mean, you will not see much of change. Okay, it's going to be a small, tiny blip in the small gate voltages, and then you have the ideal current voltage relationship. Well, as you keep increasing, you get into another type of non-ideality. After a certain voltage, you get into a certain non-linearity, which we call as high-level injection. Here, 4 is what we call as high-level injection. Okay. So, I mean, we told you, right? We said essentially Pn is a holes that are getting introduced into the n-type semiconductor. If this becomes greater than n naught, or rather, I should call it n in the n-type semiconductor, n naught. Okay. This, or you could say this is Nd. Right? Nd was a donor density. So the number of electrons in the n-type is Nd. So if Pn is actually greater than that, then we get into a regime which we call as high level injection. And the analysis becomes a little, slightly more complicated. We won't really get into it. We'll simply say that now J equal to Js exponential QV applied divided by 2 kT minus 1. High level injection. Okay. It's only applicable at very high gate voltages. In the normal gate voltages, you don't need to worry about it, but at high level, high gate voltages, you have to take into account. And we are not proving it also. We are not even trying to show you why that is. We just say that this is what it is. Okay. Otherwise, we'll have to go into all sorts of complications. Okay. The last non-ideality we can talk about is what is called as series resistance, high series resistance, or rather not high, I mean series resistance. Well, we have a PN junction, right? Let's say you have a PN junction of this form and you have a depletion region. We always worried about the junction carrier dynamics. We never considered what happens in the quasi-neutral regions. Okay, so far the quasi-neutral regions assumed to be are assumed to be having low resistivity. Low resistivity. Well, it is okay, it's a reasonable assumption for many cases, but the moment you go to very high currents, right? As you go to high voltages, you're getting into high currents. When you have high currents, effectively the diode turns out to be, in addition to this simple diode, we have a additional series resistance. So this is going to be Rp and this is going to be Rn. Okay. So this is my equivalent circuit of the diode. Okay. At low currents, at small currents, the IR drop across the quasi-neutral region is negligible. Okay. At small J, IR drop, right, across quasi-neutral regions is negligible. But once you go to large voltages, the drop becomes significant, and then current starts to reduce. Okay. Here, current reduces due to IR drops. IR drop across Rp and Rn, basically resistance of quasi-neutral regions. Okay, so that's why you have the fifth type of non-ideality that you can see. Why are we discussing all this? Well, I mean, I could simply talk about PN junctions and then say that the threshold voltage is whatever log nd by ni square and so on and finish it up. But then all these small things matter when we look at what is known as VLSI, very large scale integrated circuits. In that, all these non-idealities come into picture and we have to study it. Okay? So as part of foundation course, I just wanted to tell you the ideal diode behavior, which you have done most of the time, but we just took 20 minutes to analyze what happens, what are the different non-idealities that are present. Okay, so to sum up, these are the non-idealities which I've already written down. You can just go through it one more time. All right. So before I stop, I just want to mention one more aspect which is important, okay, which is the impact of temperature. So far in the PN junction analysis, we have not changed the temperature, but you could change the temperature. Okay, in a real device, for example, if you're taking a semiconductor chip in a computer, right? If you run it faster, or if you run it, you put a lot of load, you run a lot of computations on it, it's going to heat up. When it heats up, the junction's parameters are going to change, right? Even the threshold voltage is going to change, right? So we need to understand what happens to these parameters with temperature. And we won't really go in any depth, we'll just briefly tell you that. So essentially, if you increase temperature, as temperature increases, what happens? Carriers have more energy to cross the potential barrier. Right? So the threshold voltage reduces. Vt drops as temperature increases. Okay. What happens to reverse saturation current? Well, we showed that reverse saturation current was proportional to Ni, right? And that is going to Ni square actually. And that is going to be significantly dependent on the temperature. Okay. So as you increase temperature, now for this guy, Where should I put it? Okay, I'll put it on the top. Okay. As T increases, Ni is going to increase dramatically, and that's why Js will increase. Okay. And the last thing we need to analyze is what happens to the breakdown voltage. Well, I probably didn't introduce what is breakdown voltage. The point at which this breakdown is occurring is called as V, I can call it as VBR, V breakdown. So at that point, the current in the reverse bias has dramatically increased. Okay, right? So what happens to the breakdown voltage as you increase the temperature? Well, this is a little bit more subtle. Let's say if you have impact, if you have avalanche process, avalanche multiplication happening. Okay, so you're essentially your carrier is gaining kinetic energy and then transferring it to the lattice and creating electron hole pairs, right? But if you increase temperature, the carriers are going to scatter much more. The scattering time reduces, okay? Because of which the efficiency of the multiplication process, avalanche multiplication process is reduced, okay? So that's why as T increases, more scattering, or scattering, I should not, maybe I should write it as scattering between carriers increases. That implies tau, which is basically time between scattering events, okay? Tau scattering, basically time between scattering events reduces. That means there's more efficient scattering. And that is why this implies carriers cannot gain high kinetic energy. Before they gain, they simply collide with some other carrier and lose energy. So there is no directionality that is built up because of this repeated scattering events. Okay, so this implies breakdown occurs at larger voltages. Okay, so of course, I didn't show you the, in this picture it's difficult for me to show the VT, but in the reverse bias, if your temperature increases, the curve will look something like this. If this red curve was, or this orange curve was T naught, and this is T greater than T naught. So Js increases, VBR increases, VT reduces. Okay. So if you have drawn in the forward bias, if your normal V applied versus J, if you draw, this was your forward bias, right? This was your VT. And as you go to higher temperature, the VT will become something like this. So VT decreases as T increases. Okay, so this is the final thing that I wanted to talk about. So with that, I hope that I have covered a wide range of diode-related fundamentals. So please take your time and then study these things. We'll also post assignments which will contain some problems from various aspects that we have discussed. And then finally, I'll also upload a brief tutorial with NanoHub. Okay. Thank you so much. I'll see you in the next video.